Good day. My name is Alex Kilpatrick. I am recording this for my colleague Ricky. However, if it's not too embarrassing, I might leave it online on my YouTube channel. This is in preparation for the SST conference, and it is our study decoding Surprisal and Iconicity in American English. When I'm talking today, I'm going to be talking specifically about phonemic bigram surprisal, which is one of the many ways that you might calculate surprisal. Surprisal is this equation presented at the top of this slide. It comes out of Claude Shannon's master's thesis, which outlined information theory, which is essentially a way of creating a quantification of probabilistic information in communication systems. Let's talk about phonemic bigram surprisal first and get it out of the way. If we go through this surprisal equation, on the right-hand side, the P represents the percentage chance of one phoneme following another. So this high front vowel in American English has about a 20% chance of being followed by the velar nasal, about an 8.5% chance of being followed by the S, and almost a 5% chance of being followed by the K. The left-hand side of this equation is a logarithmic transformation. I like to think of this as a coin toss transformation, because if you were to flip one coin and it were to come up heads, which is a 50% chance, that would carry one bit of information. Two coins that were both coming up heads is a 25% chance. That's 2 bits of information. Three coins coming up heads, 12.5% chance, 3 bits of information, and so on and so forth. So we can apply that transformation to our bigram probabilities. So that 20% chance of the ing sequence carries 2.33 bits of information. We can apply this to an entire word like linguistics and calculate the surprisal for all of those bigrams. And what we talk about in this study is average bigram surprisal. And the average surprisal for each word is the sum of the total surprisal divided by the number of bigrams. And what this does is it allows us to assign a score to each word. So for example, the word linguistics has a score of 3.77. It carries an average of 3.77 bits of information. And what this does is it takes length into account, because we know that length influences surprisal information. This is a study by King and Waddell. And what they did a large cross-linguistic study where they were looking at how in all of these languages, as words get longer, the transitional probability of speech sound increases, or another way of saying it, the surprisal decreases. So they express less information as words get longer. Now, we were interested in examining this in our data set. Reminder that this is American English. And this heat map on the left-hand side shows us all of the samples. And what was interesting here is that we did see an effect of length on that first bigram and the last two bigrams, where it's really clear. But in the middle, for those longer words, there wasn't a really clear pattern of the influence of length on surprisal, which is kind of interesting. Now, the first bigram and the last two bigrams, we considered the possibility that this is due to prefixes and suffixes. So we accounted for that in the second model, which is on the right-hand side, where we included only those samples that were monomorphemic, so just samples with a single morpheme. We see that the pattern still exists, so it looks to be the first bigram and the last two bigrams, but obviously that's quite attenuated. However, the pattern still exists and it's still statistically significant. So there's something going on here where it's not just at the beginnings of words that we see this decrease of information as words get longer. We see it at the ends of words as well, which might be signaling something like word boundaries, but that is for a different study. Syllabic surprisal is a different way of calculating surprisal. Syllabic surprisal is calculated on the possibility of all speech sounds within a syllable. Christoph Koop and colleagues what they did is a cross-linguistic analysis of syllabic surprisal for, I think it's 17 unrelated languages. And then they cross-checked that with the speed at which the languages were spoken. And something interesting came out of that, whereby essentially each language seems to converge in how much information is expressed over time, that being 39 bits per second. So we have some languages that are spoken much faster than other languages. And at two ends of this spectrum, we have the relatively slow English, which is a little bit over 6 syllables per second. We have the much faster Japanese, which is a little bit under 8 syllables per second. But the difference between these languages is that English has a larger phonemic inventory and a much less restrictive phonotactic system. So what happens is that English has many, many more possible combinations of syllables. Now, when you have more possible combinations of syllables and more phonemes, what happens is that your phonemic bigram surprisal or your syllabic surprisal, the average surprisal will reduce for each of these. And what will happen is you'll end up with different levels of information. So for English, we have about 7 bits of information per syllable. And for Japanese, we have about 5 bits of information per syllable. So what's happening is these faster languages tend to have less information per syllable. The slower languages tend to have more information per syllable. And we see a convergence in how much information is expressed over time. This study has garnered my attention for some time. I think that it's an important finding because it kind of speaks to the cognitive limitations that we have in language. A question that has been very interesting to me for some time is why don't humans speak faster than they do? Because we can speak faster and we are reasonably good at at understanding rapid speech. One of the ways that I look at this is through cognitive load theory. And cognitive load theory is this idea that within cognitive load theory, we have this idea that highly predictable events or experiences are much easier to process. And we see this across a range of psychological studies, where what we observe is that when a stimuli is a highly expected, then it is processed faster and more accurately than an unexpected stimuli. One of the other interesting things to do with expectedness is outlined in the lossy context surprisal model, which posits that the extra effort that required to process unexpected stimuli deeper encodes that stimuli in your long-term memory. So the lossy context surprisal memory, it's this idea that we don't have a perfect encoding of memory. We kind of prioritize certain events and experiences, and it seems to be that more surprising events and experiences are encoded more deeply in our memory. So, for example, this sentence, the child ate an, we might make any number of predictions for the word that is coming up, right? We might say an apple or an ice cream. However, when the word is unexpected, such as an eggplant, then what's going to happen here is this word is consuming more of your cognitive resources than, say, apple, because it's an unexpected word. You are reading it, you are processing it slowly. You are more likely to make a mistake in your processing of it. However, because it's unexpected, it's being more deeply encoded into your memory. And there's many experiments that look at this for both in terms of the cognitive load of the event and also the memory retention of it. However, this is a sentence level examination. And in this study, this is the first to look at a within word probability examination. So what we're doing is we're kind of observing the effect of the percentage chance of the phoneme rather than the word. And what this does is it, as I said earlier, allows us to assign a score to the word and then cross-reference that word with a different data set. or many other data sets as we do in this study. The other side of this coin is iconicity. Now, iconicity is the sound symbol, the form meaning associations between words and their meaning. Examples of this is the mill-mal effect, where the high front vowels typically represent small objects and the low back vowels typically represent large objects, or the kiki-boober effect, which is the idea that some sounds, such as those found in kiki, are sharper than the more rounded sounds of bulba. These are examples of iconicity. The reason why we wanted to include iconicity into this study is because iconic words are, because there is a form meaning resemblance, iconic words are processed more easily, more readily, more rapidly, more accurately than arbitrary words. They're also remembered better. So there's a number of studies that point to the linguistic efficiency, you might say, of iconic words, where they facilitate faster processing, more accurate processing, and increased memory recall. So essentially, we include iconic words here as a benchmark to examine the effects of phonemic bigram surprisal. So our method, we took a very large corpus of spoken American English, 8 minutes, 9 minutes up to now. Okay. We took a very large corpus of spoken American English, 54 million lexemes, and cross-referenced that with the CMU pronouncing dictionary to get the standard American English transcriptions for each word. And using that, we were able to calculate surprisal. And average surprisal. So once we had average surprisal assigned to each word, we were able to cross-reference that data set with iconicity ratings, which are taken from Bodo Winter and colleagues' iconicity ratings, where American English speakers assigned scores to words according to how much they felt that each word sounds like its meaning. We have morpheme counts, and we also have parts of speech in there as well. We then cross-reference that master data set with the results of a battery of psycholinguistic experiments. So we have an auditory lexical decision task experiment, a read aloud experiment, a memory recall experiment, and 2 age of acquisition experiments. If you're interested, the full data for this study and instructions on how the data was engineered available in the OSF repository. So the first thing we did is we constructed a multiple linear regression model with average surprisal as the dependent variable and everything else except the psycholinguistic experiments as the independent variables. So we have things like phonemic length, iconicity scores, the interaction of length and iconicity, the number of morphemes, and the parts of speech. The general hypothesis we were testing here is if longer words are more difficult to process and iconic words are easier to process, then the influence of length on information expression should be attenuated in iconic words. And we see that indeed, longer words express less average information and iconic words express more average information. But that effect of length on surprisal is explained entirely by the interaction of iconicity and length in this model. I want to make the caveat that that's probably not the case. I think that it's an artifact of the data here. Other models that I've run are both length, iconicity, and the interaction effect of length on iconicity. All of them are significant. Here in this model, however, length is not significant. So the influence of length is explained entirely by its interaction with iconicity. Yep. Next, we ran 7 multiple linear regression models with the psycholinguistic experiments as the dependent variables. This is similar to the previous model. However, we include average bigram surprisal. Here it's noted as informativity. And we can take a close look at this in a moment. The hypothesis here is that words that carry more information, so high average bigram surprisal, are more difficult to process, but are easier to remember. and words that are highly iconic are both easier to process and are easier to remember. So here we can take a closer look at that. We see that in the lexical decision task, the influence of average bigram surprisal on the accuracy, there's a negative correlation here. So increased information, decreased accuracy, and it increased response time. And iconicity had the opposite effect, where increased iconicity, words that are more iconic, increase the accuracy and decrease the response time. So highly informative words, words that carry a lot of information, increase processing difficulty. Those that are more iconic, decrease processing difficulty. We see the exact same pattern in the reading task, where increased information decreases accuracy and increases response time, and increased iconicity increases accuracy and decreases response time. In the age of acquisition experiments, we see that increased information, average bigram surprisal, this increases the age at which words are obtained, acquired, and iconic words, on the other hand, are associated with a lower age of acquisition. And lastly, we have the results of the memory recall experiment. And this was quite interesting. Here we have increased information associated with increased memory recall, and increased iconicity also associated with increased memory recall. So what does this mean? It means that more informative words are harder to process and impose a heavier cognitive load, while words with iconic associations are easier to process and constitute a lighter cognitive load. However, both iconic and informative words are easier to remember. So the general conclusion here is that words with higher average surprisal are more difficult to process. Iconic words are easier to process. Iconic words carry more information than arbitrary words. Perhaps this is a way to quantify their markedness. We can talk about that later. Maybe I should talk about that earlier. Iconicity facilitates memory recall, but so does increased information, and both cognitive load theory and the lossy cognate surprisal model can predict the outcomes if we extend them beyond the sentence level processing that they've been used for thus far. I'm sure there's stuff that I've missed, and we have a number of months before the conference, but that's the general idea. Let me know how you feel.